So this says the notation dy dx is read as the derivative of y with respect to x, or simply dy dx. Don't mind those dollar signs there, okay? Using the limit notation, they just throw everything right there. Again, what they haven't done is our limit notation, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. So those are all the same thing, okay? All right, so again, throughout this book, you're going to see these links right here to interactive examples. You can download the Wolfram CDF player onto your computer for free. I believe it's also downloadable on like iPads and iPhones. And what that's going to do is you're going to be able to download a file, open it using the Wolfram CDF player, and it gives you an interactive version of this problem right here. You can see what's going on. You are not required to download these. You are not required to go through these little things, but if you're a visual learner, I like seeing what's happening. If you're a visual learner, these interactive examples can help you a lot. So if you have the time, please go ahead and look at those, but let's go ahead and look at the problem. It's not necessary to solve the problem to look at those interactive examples. It says, find the derivative of f of x equals x cubed plus 2. Use the definition of derivative. And I can't express enough what it says in this problem. It says use the definition of derivative. Any time you see that, you must use the limit as h approaches 0 of f of x plus h minus f of x all over h, or the delta x version. I don't care which version you use, but you must use the limit process, and you must show every step, and show every step. Okay, this problem, I'm going to start doing it in the previous ones. We did it in 5 separate steps, right? We found f of x plus h, we subtracted off f of x, we divided by h, then we found the limit. I am now going to merge all those steps into one. If you noticed on the previous examples, I never used equal signs when I went from step to step because those steps weren't equal. I only used equal signs within a step, but I never started off with an equal sign. Well, what I want to do is do everything together, all at once, and you'll see how essentially you're doing the exact same thing. The steps 1, 2, 3, 4, you're just writing a lot more all in the same line. So you can do it the previous way, where we break it into individual steps. That will always work, and I will always accept that as long as you label your steps. Or you can do it like I'm going to do now, which is inline. So what do I mean like that? Here's what I mean. We know that we have to find the derivative, f prime of x, which is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That is the definition of a derivative. Well, now what I'm going to do is I'm going to put an equal sign, and because it's an equal sign here, I have to rewrite every single part of it. So I have to write the limit as h approaches 0, and now what I'm going to do is plug in x plus h. I'm going to find f of x plus h. So let me use some colors here to help you see what's going on. I'm going to find this part first, and I'm going to find that part second, right? Okay, so let's find f of x plus h. Well, that would be x plus h quantity cubed plus 2, wouldn't it? Okay, so instead of x cubed plus 2, it would be x plus h quantity cubed plus 2. Then we have to subtract off our original function being in parentheses. It has to be in parentheses. So that would be the x cubed plus 2, right? Okay, I don't know why I put that. Let me erase that one parenthesis I just put there. That'd be the x cubed plus 2, and then all of that's over h. So instead of doing it in 3 individual parts, I'm putting it all together, all in line. All right, we need to do some side work here, because what we need to do is we need to expand x plus h quantity cubed. And I don't know if you remember how to expand that, but it's not too easy. You need to do quite a bit of work. So I'm going to do that on the side here over in green writing. So I'm looking at x plus h quantity cubed. Well, really that's x plus h times x plus h times x plus h, right? X plus h 3 times. So what I'm going to do is I'm going to FOIL out these two right here. This would be x plus h times, well, x times x is x squared. X times, that's the, sorry, first outer would be xh, inners would be xh, so that's plus 2xh. And then last, h times h is h squared. Okay? Now what I'm going to do is I'm going to distribute the x through to every problem. So let's distribute just the x through. X times x squared is x cubed. X times 2xh would be 2x squared h. X times h squared would be plus xh squared. Now I'm going to distribute the h through to each of those terms. So when I distribute the h through, I'd have x plus x squared h. Then I'd have plus h times 2xh would be plus 2xh squared. And then h times h squared would be h cubed. Let's see if we can combine like terms here. Looks like I have a 2x squared h plus an x squared h. And I have an xh squared plus a 2xh squared. So foiling that out, I would get x cubed plus 3x squared h plus 3xh squared. And then I'd have plus my h cubed on the end. So that's what I'm going to plug in for just this part right there. Okay, that's a lot. I know it is. But let's go ahead and plug that in. So this is the same thing as, let me get to black, the limit as h approaches 0 of all of that mess. So that was x cubed plus 3x squared h plus 3xh squared plus h cubed. That's just the green part, right? I'm still in the red here. And then I still have that plus 2. Never forget that plus 2. Okay? And then I have to subtract off that whole blue part. But what I'm going to do now is I'm going to distribute that negative to each of those blue parts. So that's going to be a minus x cubed, let me use black, minus x cubed, and then distributing the negative to the 2 would be a minus 2. Why did I distribute that negative? Because hopefully now at least a couple of things cancel, and indeed they do. The x cubes cancel, and the 2's cancel. So I'm left with, it's a lot to say, bear with me, the limit as h approaches 0. Notice I'm writing equals every single time. I'm writing the limit every single time. On top, I would have 3x squared h plus 3xh squared plus h cubed all over h. Well, what do I realize now? Now I realize I need to factor out an h from each one of those terms. So this is the limit as h approaches 0 of h times 3x squared times h divided by h would just be 3x squared. The next term is 3xh squared divided by h would be just 3xh. And the last term is h cubed divided by h would give me an h squared. So when I factor out the numerator, I should have h times the quantity 3x squared plus 3xh plus h squared. All of this is over h. Okay? What do? Simplify the h's. We had to factor before we could simplify. Again, we had to factor before we could simplify. So we're left with the limit. Notice I put an equal sign. I still have my limit. The limit as h approaches 0 of what's left. When we cleaned it all up, we ended up with 3x squared plus 3xh plus h squared. That's the final simplified version. Okay, what do we do now? Now we plug in 0 for h. So anywhere we see an h, we're going to plug in a 0. So this would be equal to, now I don't write my limit sign because I'm actually evaluating my limit. So every single step I've had to write the limit as h approaches 0. This is the one step that I get to stop writing the limit as h approaches 0 because I'm actually evaluating the limit. So this would be 3x squared plus 3x times 0 plus 0 squared. Again, 3x times 0 is 0, 0 squared is 0, so I'm left with 3x squared. So what is the derivative of f of x equals x cubed plus 2? All of that work tells me the answer is 3x squared. That was a beast of a problem algebraically where there's so much work that you had to show. There's a lot of expanding you had to do, a lot of things that you can mess up. But what I want to do here is I want to point out a couple of things. First thing, why the heck did we do this whole entire process? Well, if all we wanted to do was plug in 0 for h. Look back at the beginning. If we plugged in 0 for h, we would have had x cubed plus 2 minus x cubed plus 2 all over h. We would have had 0 on the numerator, 0 in the denominator, would have been undefined, the limit doesn't exist, so as we know, we'd have to keep on going. Same thing here, if we plugged in 0 for h, we would have ended up with 0 on top, 0 on bottom. Same thing here, 0 on top, 0 on bottom. Same thing here, 0 on top, 0 on bottom. So we had to do all of that simplifying so we could plug in 0. We could not plug in 0 at any step prior to the step that we did, or it wouldn't have been defined. So you had to do each and every one of those steps, all of that simplification first, to be able to plug in 0. Plugging in 0 is the easy part. So again, how much of this problem is actually calculus? Here's the calculus right here in that last step. Wherever you see an h, plug in 0. That's the only new thing that you didn't know in college algebra how to do on this problem. Every single other step of this problem was just algebra. So this really drives home the point that I tried saying in the algebra review and the lines and functions review is calculus. 90% of calculus is algebra. More than that, 95% of calculus is algebra. Calculus is very, very easy. All we did was plugged in 0 for h. That's literally all we did. That is the only calculus that we did in this problem. All the rest of it was algebra. So it's not calculus that's difficult, it's the algebra in calculus that's difficult, okay? If you have those algebra skills, the calculus part is easy. So make sure you're tuned up on your algebra skills. Okay, again, this is what I call inline, where you have the limit as h approaches 0, and you do the entire thing every single time. Some students like this because they just like seeing it being done. This is the type of stuff that you're going to see when you look at the solutions in the textbook. They're going to do it inline, where every single part of it is inline, okay? I am perfectly fine with you, If that was biting off too much all at once, doing it in the 4 or 5 steps that we talked about previously. Just show step 1, then step 2, then step 3, then step 4. Get your answer perfectly fine. I don't care which way you do it. All right, we're going to look at example 4 now. I want you to star this example. The reason being is this is very close to what could be on the test. Finding the derivative of f prime of x, really, really important here. Again, you must use the definition of derivative. So you must use the limit as h approaches 0 of f of x plus h minus f of x all over h. I am going to teach you rules in the following sections that make this significantly easier. You don't have to do the limits forever, but most certainly in this entire section and on this test, if it says definition of derivative, you absolutely have to use the definition of derivative, okay? Every step of the problem. So it says find f prime of x for f of x equal to the square root of x. Then find the slopes of the graph of f at the points 1, 1 and 4, 2. Discuss the behavior at 0, 0. So let's get started with us. They want us to find the derivative. So we're going to find f prime of x, and we know that equals to the limit as h approaches 0 of f of x plus h minus f of x all over h. If you're using the definition of derivative, write the definition of derivative. Yes, I do expect you to physically write it down on your paper. Okay, I'm going to do this inline, like I did on the previous example. If you want to do it in separate steps, that's perfectly fine. So this is the limit as h approaches 0 of, well, f of x plus h is go to your original function. Wherever you see an x, you're going to plug in x plus h. So that would be the square root of x plus h minus, and that's the red part, right? There that is. Now we have the blue part right here. So that would be f of x, which is just the square root of x, all over h. So there's f of x plus h minus f of x all over h. Again, let's think about evaluating that limit. Could we plug in h equals 0? Well, if we plugged in h equals 0, we'd have the square root of x minus the square root of x, which is 0, all over 0. So that's 0 over 0, indeterminate form. Well, what's the beauty of this? In the previous section, you already did this problem. You already did a problem almost exactly like this when you were doing the limits. You already did a problem on your first test almost exactly like this problem right here. The only difference is we've added the limit as h approaches 0. That's really the only new part. So hopefully you remember how to handle a limit like this. When you get 0 over 0 in its indeterminate form and you have radicals, hopefully you're thinking about the previous test that we took where the trick was to multiply by the conjugate of the numerator. It's called rationalizing the numerator. So this is where you would multiply it times the square root of x plus h plus the square root of x in both the numerator and the denominator. Hopefully you remember that. The square root of x plus h plus the square root of x on both the numerator and denominator. Okay? So this equals the limit as h approaches 0. And again, a lot of you had problems showing your proper work in this section, so make sure you're showing every single step. So let's think about foiling this. The square root of x plus h times the square root of x plus h is the square root of x plus h squared. Then you would have plus the square root of x plus h times the square root of x. Then you'd have minus the square root of x plus h times the square root of x. So those two middle terms are always going to cancel when you FOIL out the multiplication of a conjugate. And let's be careful on this last one. It's going to be minus the square root of x times the square root of x. So that's going to be minus the square root of x squared. So that's the numerator FOILed out. In the denominator, never FOIL it out. Always leave it in factored form. Okay, so that's h times the square root of x plus h plus the square root of x. We'll look at the first one. Square root of x plus h squared is just x plus h, and the square root of x squared is just x. So this is the limit as h approaches 0 of x plus h minus x all over h times the square root of x plus h plus the square root of x. Okay, great. Now, what happens? We need to try doing our simplifying. Well, a lot of you are going to see that the x's cancel, and then you're going to think the h's simplify. The h's do simplify, but you absolutely cannot do this mathematically in one step. You have to cancel the x's first, and then in the next step, the h's simplify. Mathematically, we cannot simplify those h's until they are factors. And at this point in time, h is not a factor of the numerator. So you absolutely have to do this in two separate steps. This is the limit as h approaches 0 of if those x's canceled. Now we have h over h times the square root of x plus h plus the square root of x. We had to do that in two steps. The h's now mathematically simplify. They did not simplify before. So this is equal to the limit as h approaches 0. Notice I keep saying simplify. I say simplify because they turn into a 1, not a 0. And this would be 1 over the square root of x plus h plus the square root of x. So I have now simplified it as much as I can. Now that it's simplified, the question is, can I plug in h equals 0? Can I evaluate my limit? So this equals, notice I've had my limit every single one of these steps. Now that I'm evaluating the limit, I'm going to get rid of the limit as h approaches 0. And I have 1 over the square root of x plus 0 plus the square root of x, which is 1 over root x plus root x, which is 1 over 2 root x. So this right here is our slope of the tangent line at any given point, which is also the derivative of the function. 1 over 2 root x. You give me, let me go to black. You give me the x value, I give you the slope of the tangent line, which is the derivative. We just did that limit process in line. The trick here was multiply by the conjugate. That's the trick. Multiply by the conjugate. Just as you did in the previous section, I have to see that work. I have to see every step. So we're not quite done. It wanted us to evaluate it at the different points. So let's consider here. We know that f prime of x is 1 over 2 root x. We need to consider it at the two different x values. The first x value they give us is 1 because it's the point 1, 1. The second x value they give us is 4. So let's look at this. It would be 1 over 2 times the square root of 1, which would be what? 1/2. So at the point 1, 1, our slope would be 1/2. or the derivative is what they asked for, which is the same thing as the slope of the graph. At 4, it'd be 1 over 2 times the square root of 4. Well, the square root of 4 is 2. 2 times 2 is 4, so I'm getting a value of 1/4. So we were able to find the derivative using the definition of derivative. We were able to find the derivative at points, which is the same as the slope of the tangent line at those points.